Good morning to one and all. So today, as a continuation of this CO2, that is analyzing CPU scheduling mechanisms for diverse scheduling criteria, we are going to discuss upon the different types of scheduling algorithms. So among the different types of scheduling algorithms, the first one that we are going to discuss today is about first come first serve scheduling. In short, it is abbreviated as Fcfs. So this, as the name suggests, whichever process which comes first inside the CPU or the processor to get executed, that will be processed first by the CPU. So first comes, first serve. Which one is coming first will be served first. So that is the main um, agenda of this first come first serve scheduling. This is the way in which it will operate, and the main uh, the main point that we want to focus here is this FCFS scheduling is a non-preemptive scheduling. So as we have discussed earlier, a non-preemptive scheduling is something in which a process is never forced to be taken out from the CPU for its execution. So such until it completes its execution, the process it will remain inside the CPU, and only after its completion we can take it out. So only then the next process will enter into the CPU. So this is how the first come first serve scheduling it operates. So these are the points which I have pointed out here. It is a non-preemptive scheduling algorithm (FCFS), and the processes are executed on the first come first serve basis. You can just relate it with a FIFO queue. So let's take an example of a real-time example, as we collect a ticket from a ticket counter by standing in a queue. So whichever person who enters the queue first will be standing at the first end, that is the head. So the person from the head will be getting the ticket, and he will move out of the queue, and the one who is standing next to the first head, the person after that will be served the next. So whoever comes as a new to this queue, they will be joining the queue only at the tail end. So one who is at the head will get the ticket first, and one who is at the tail will be the newcomer here. So as and when each person gets a ticket and move away from the queue, the other person who is standing behind them, they will be getting the opportunity. So as we stand in a queue in a real time, the same way our processes will be processed in case of FCFS scheduling. So this example, let's see this with an example. So here there are three processes P1, P2 and P3. So this example I have taken to tell you how a longer process which comes first for its execution, it occupies a more amount of time, so that the very short processes which are having only burst times of just 3 milliseconds are waiting for so long to get the CPU for their execution. So just to give a comparison, I have taken this example. So let's consider three processes P1, P2 and P3. So we are now assuming that all these three processes are arriving to the CPU at time 0. So the arrival time of all the three processes are only 0. So the point here is all the processes are ready for execution at time 0 itself. So they don't want to wait. Actually, they don't want to wait. So that is a point here, because they have arrived, and so the scheduler is now ready to schedule any process um, among these three processes. But as this is FCFS scheduling, the first come the first process which has come, it will be served first. So as per our ID, process ID that we have listed here, the first process is P1, which is having a burst time of 24 milliseconds, and P2 is having a burst time of 3 milliseconds, and P3 is also having a burst time of 3 milliseconds. So now imagine, as we say, the first process, that is P1, which is having 24 milliseconds of burst time, it has been given to the processor and it is getting executed from time 0 to 24. So it is taking totally 24 milliseconds of time and on a whole. And only after these 24 milliseconds, the second process is being given to the CPU for execution. So the thing that we want to note here is, even though the burst time of this P2 is very small, it has to wait for the first process to get its completion, because this is a non-preemptive algorithm. So only when the first process P1 it comes outside the processor, P2 can be given inside. So we are giving P2 at time t24, and it is having a burst time of 3, so that it's executing from 24 to 27. And now we are after, at 27th millisecond, we are giving P3 to the processor, and now P3 is getting executed from 27 to 30. So overall execution time that all the three processes took is from 0 to 30. But P1 has taken 24 milliseconds, P2 it has waited for 24 milliseconds, and then it has got the CPU's control, and then P3 has waited up to 27 milliseconds, and then only it has got the CPU's control. So this is how we are getting the Gantt chart. This is the Gantt chart which we usually plot, so that we can easily track the different waiting time and the turnaround time of each and every processes, and the completion time can be easily calculated from this Gantt chart. So as we can see here, the process P1, so waiting time is 0, because it has not waited for any time for any other processes to get its completion. But process P2 waiting time is 24, and process P3's waiting time is 27. It has waited up to 27 milliseconds to get the CPU's control. So the waiting time of P3 is 27. And similarly, the completion time, P1 has completed by 24th millisecond, P2 by 27th millisecond, and P3 by 30th millisecond. So while calculating the turnaround time, usually the turnaround time is the completion time minus the waiting time, the arrival time. So all the processes has arrived at time 0. So P1 has the completion time of 24, P2 has a completion time of 27, and P3 has a completion time of 30, as we have seen here. So the turnaround time can be calculated by average turnaround time can be calculated by averaging all these three. So 24 plus 27 plus 30 divided by 3, it will be giving 27 milliseconds, and the waiting time is the average of these three waiting times, so that we are getting 17 milliseconds, right? So now, by just changing the order of the incoming processes. So in this example, we have seen that the process has arrived in the order P1, P2, P3. By just changing the order from P1, P2, P3 to P2, P3, P1, we can see a massive difference in the waiting time and the turnaround time. So let's see now. So the same um, burst time has been taken here. P1 is having the same burst time of 24, P2 has 3 and P3 has 3. The one thing that we have changed is the order in which they have arrived. So in the previous example we have taken the arrival order as P1, P2, P3, but now we are taking the arrival order as P3, P2, P1. Reverse order we have P2, P3, P1, right? Now P2, it is having a burst time of 3. So starting from 0, and the same assumption, that is all the process has arrived at time 0. Now P2 is having a burst time of 3, so from 0 to 3 it will be executing in the CPU. And the next process as per our order change is P3, so that the P3 will take the hold of the CPU by 3rd millisecond itself, and it will be executing for another 3 seconds. So it will be uh, completing its execution at time 6th millisecond, and at the time 6 itself, 6th millisecond, P1 can get the hold of CPU, and it will be executing till 30, because it is having a burst time of 24 milliseconds. So totally it will be taking 30 milliseconds to complete. So when we compare these two, the overall execution time is the same, the 30 millisecond, but the order in which they arrive, it creates a massive difference in their waiting times, because the short processes have taken the hold of the CPU at the first turn itself, whereas the longer process is taking the hold only after these two processes are getting its execution done. So this can be very easier for us, and so because the shorter processes has completed its execution at very sooner. Okay, so now when we calculate the waiting time of P1, P1's waiting time, actually P1's waiting time is actually 6, and P2's waiting time is actually 0, and P3's waiting time is 3. It's not mentioned here properly, but actually this is the waiting time of P1, P2 and P3, and completion time of P1 is 30, and completion time of P2 is 3, and completion time of P3 is 6. And when we take a sum of all and the average of all, we can see that the average waiting time is 3 and average completion time is 13, whereas it was 17 and 27 in the previous case. As we have seen here, it was 17 and 27 in the previous case, and just by differing the order, we have reduced the waiting time and completion time to a very greater extent. So whenever the shortest jobs it gets struck, and in order to execute, in order to get the hold of the CPU, due to a very long process, they have to be waiting for a very long time. Such a effect is called as convoy effect. The 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 way in which that processes have been stuck, so that the shorter processes are stuck, so that the longer process is taking its execution, is doing its execution for all the time, they are being waiting in the ready queue to get the hold of the CPU. So such effect is called as the convoy effect. So at that time the performance is heavily, it is depreciating. So in order to improve the performance, so just by changing the order, we can improve the performance of Fcfs algorithm. So because of its non-preemptive nature, and also due to the longer processes, longer burst time processes arriving at the first, the performance is highly depreciated.